So it's our Rtos workshop. So our agenda, first we're going to go over what an Rtos is, then we're going to go over some key Rtos features, especially for free Rtos, like task scheduling, mutex and semaphores, and queues. And then we're going to do some actual code examples that you guys can follow along with yourselves for use cases for scheduling semaphores and, or not semaphores, mutexes and queues. And at the end, we'll finish off with Q&A. So first of all, what is an RTOS? Basically, RTOS stands for real-time operating system, and it's just a piece of software that helps you run applications really reliably and within critical time constraints. And so some of the main features of an RTOS should be that it should be deterministic, so your system's responding to any external inputs within predictable time frames, so that you're able to validate your software and know that it works instead of it being it worked this time, but now this time it does not meet the deadlines. And it should also allow your software to meet any hard deadlines and respond quickly to any external events, like on our satellite, like if we have over temperature event or over current event, we should be able to deal with those events quickly. Otherwise, it's GG. And also it allows you to run multiple tasks concurrently. And we're going to talk a bit more about this later and what a task actually is. Okay, so what's the difference between an RTOS and a general purpose OS like Windows or Mac? The main difference is just deadlines. RTOSs are designed to be really strict with their timing requirements and making sure that you're gonna meet your deadlines and get whatever you need done in time. For example, if you're editing a spreadsheet on your computer, like on Windows, and your thing starts lagging, it doesn't really matter. Nothing's gonna happen. You're not gonna die, as long as it gets done eventually. It doesn't matter. But with an RTOS, there's a lot of times, like in a real time system, where you need it done in time, and just doing it eventually isn't enough. All right, so now some key RTOS features. First thing is concurrency. So that's basically just the concept of having multiple pieces of code running or appearing to run at the same time. So single core processors can only actually execute one thread at a time. So it just executes it sequentially. But with an RTOS, if you have multiple tasks, it lets you do them concurrently. So you can do a little bit of one task and then switch to another task, start running a little bit of that, and then jump to another task, start running that. So we rapidly switch between multiple tasks to make it look like they're all running at the same time when really it's just one running at a time. So yes, we do it concurrently, but not simultaneously. You can do it simultaneously if you have multiple cores, but with single core machine like we have, it's concurrent. So all tasks are making progress, but they're not making progress at the same time. For example, if you were cooking a meal, you could do it in a sequential fashion where you start cutting vegetables, finish some vegetables, then start cooking meat, and then finish cooking the meat. And this would be if you weren't having any type of concurrency. But if you do it concurrently, you start cutting some vegetables. Oh, I wrote that wrong. But you could start cutting some vegetables, and then while you're doing that, start cooking some meat as well, and then finish the vegetables while you're waiting for the meat to cook, and then finish cooking the meat after you're done that. So it kind of avoids you just spending time not doing anything else because you're waiting to finish one thing. Yeah, and this kind of shows it. So you can see here, we have their scheduler, and then we have task 1, task 2, and task 3. These little blocks show the CPU usage. So at first we have task 1 using the CPU for some time, and then it switches to running task 2 for a same amount of time because it's a round robin, which we'll talk about later. And then task 3 starts running again, then it switches back to task 1, and so on. And you can also see here it shows the difference between sequential concurrent and parallel. So with sequential, you basically just go in a like a straight sequence from start to end. There's no like jumps. But with concurrent, imagine these are like two different like threads being executed. With concurrent, you can go here, jump to the other task, jump back, jump forward to the other task again, and just do that until you finish. And with parallel, you just have both of them going at the exact same time. All right, so I've been talking about tasks, but what actually is a task? Um, it's basically just like a discrete units of work that can be executed independently in a software system, and there you can run multiple tasks concurrently. So it's just like a piece of software that you choose to like run. Um, and the way in FreeRTOS that you define tasks is with a callback function. So when you create a task and FreeRTOS decides to run the task, it calls a callback function to start it, and then whenever we switch to another task, it'll like make sure that when you start again, you start at whatever line of that you're at. And so usually you want to have these run in an infinite loop because you're gonna want your tasks running for the whole time, most of the time, but not always. And when you have tasks, you have like isolation, not complete isolation between memory, but the memory is partially isolated. So if you guys remember from the C workshop, your program will have like a stack, and there's also a heap, and there's instruction section, data section, and like a bunch of other sections. But with tasks, each task, they'll be sharing the same heap. We don't use the heap on ours, but like in general, tasks will share the same heap, but each of them will have their own task. And so you'll see that later when we do the examples, how we're defining like the stack size for each task. And then when the scheduler, which we're going to talk about later, decides that it's time for a new task to run, it triggers something called a context switch, which is what is basically just what we do when a context switch happens is we want to save all the information about the task that's currently running, like stuff like which line of code are we executing right now, all the different registers that it's using, and all the different values. Saving stuff like the stack pointer for like where we're gonna put the next thing that we put onto the stack. And then once we save all of that, then we start restoring all of the new task information. So you'll start restoring like where the task is at and start executing from there. Restore the new task stack pointer and all of its registers. Yeah. Does anybody have any questions up to this point? Feel free to unmute. Okay. All right. Feel free to stop me if you guys have any questions at any point. So these tasks are always in like one of several states. You can see this diagram over here for how FreeRTOS does it. And different RTOSes could have different possible states. Like instead of having four, they could have like 8 here. It depends on how they feel like doing it. But we'll talk about FreeRTOS in specific here. So for FreeRTOS, there's four states that a task can be in. First one is running. So there's only one task that can be in this state at a time if you're running on a single core processor. Because remember, like I mentioned, even though the tasks are running concurrently, only one task is actually like taking up the CPU time at a time. So you only have one task in the running state, which just means that it's the task being executed right now. And when all, actually, I'll mention this later. And then there's also the ready state, which means that the task is ready to be run, like it wants to be run, and it's telling the scheduler that it should be scheduled at like the earliest convenience, but it's not it's not been scheduled yet. So eventually, the scheduler should um, move that state from move that task from the ready state into the running state and start executing it. And then there's also the block state. So this happens whenever you take like a mutex or semaphore and it's not available, and you decide to make make it blocking, which we'll talk about later. But in this state, the task is basically just it's waiting for some kind of event, and usually you'll have a timeout as well. And until that event or that timeout doesn't happen, whichever one comes first, is telling the scheduler that it shouldn't be scheduled. So this task, while it's in this block state, won't be taking up any CPU time because the scheduler is not going to choose it to run. So it's just not going to run until that event or that timeout happens. And then finally, we have the suspended state. So this just means that the task shouldn't be scheduled for some indefinite amount of time. So the difference between blocked and suspended is when you're in suspended mode in FreeRTOS, you have to explicitly call vtask resume to get it back into the ready state. And also, when a task is blocked, it typically should have some kind of timeout when it will become unblocked, even if like the event is waiting for it doesn't happen. But if there is no timeout, then it's always suspended. Yeah, because suspended tasks have no timeout. They could just like never get ran ever again. And also another thing to note is when there's no task that's ready to be ran, like let's say we have like three tasks in our system, and they're all blocked right now. They're all just waiting for some kind of timeout before they start running again. We need like the CPU is not just gonna be like just waiting and doing nothing. It runs something called the idle task, um, which is defined usually by your RTOS, and it will just put the idle task in the running state. And like if you ever looked at your OS CPU usage, you might see sometimes like it says like idle had some CPU usage, and that's what that is. That just means no other task is ready to be run, so it just runs idle task. Okay. So it's now scheduling. So scheduling is basically the scheduler is what decides which tasks get to be in the running state and when to switch to a new task and what the new task should be. So like we mentioned before how we have context switches to switch to new tasks. That's decided by the scheduler. So there's a lot of different algorithms that like are implemented in RTOSes and also regular OSs depending on what you need. So I'll just like give a few examples, but we're not going to go into detail into all of these, but you can look them up yourself if you're interested. So the one FreeRTOS uses is called fixed priority preemptive scheduler. And then there's also cooperative scheduling, earliest deadline first, and then what Linux uses is the completely fair scheduler. So you guys can look into that yourselves. But yeah, so basically the scheduler just, let's say we have some tasks running, it decides when we want to stop running that task, and also what task we want to start running next. And then it triggers the context switch to switch to a new task. And the scheduler, the main thing is that it needs to make sure that all tasks are given a sufficient amount of time to run to meet their deadlines. Because, like, let's say we have a bad scheduler, we could have some tasks that just never end up running if your algorithm isn't good. And obviously, you don't want that. All of your tasks should be ran at some point, and they should have enough time to run. So that's kind of like a requirement on people who design schedulers to make sure that there's no tasks that are like we call it like starving of CPU time. It's task starvation. So you want to make sure that all tasks get some time to run. And yeah, like I mentioned, FreeRTOS uses something called a fixed priority preemptive scheduler with round robin time slicing by default. That sounds like a lot of words, but I'll explain it on the slide right now. Okay, so what does this mean? I'll break it down by words. So first of all, the fixed priority part means that each task will have like a numerical priority assigned to it when you create it. So in our actual software, when we create the task, we assign some priority level to it, and higher number means higher priority. And so the fixed part just means that the scheduler won't permanently change its priority, but it could do it temporarily. And preemptive means that any task that's running could be moved into ready state to allow another task to run at any time if a higher priority task becomes ready. So that's called getting preempted. So the scheduler is always going to run whatever the highest priority task um, is in the ready or running state. And if a task is running and the higher priority task becomes ready, then the current task gets preempted and the higher priority task starts to run. So if we had like a task that was at like priority level 2 and we had another task at priority 1, um, and let's say that task at priority 2 just never blocks. Like let's say we have like a while one loop, so it never blocks. Rtos will keep that task in the running state and just never end up scheduling uh, the task that had priority 1 because the first one hasn't blocked. But if it were to block on something, then it would switch back down to the task number 1. And like I mentioned earlier, the null task that would be at priority level 0. So if the second if this priority level 2 task is blocked and then the priority level 1 task also blocks, then it would just run priority level 0, which would be the null task. And then we have round robin time slicing, which is what happens when you have multiple tasks of the same priority that are all ready to run. They start sharing CPU time, so you kind of like they each get their own slice of time of CPU time, and it's like done in a round robin fashion. So if we had 3, we're gonna like switch, like loop through each task, like iteratively. So if we have 2 tasks that are both the highest priority ready tasks, then the scheduler will choose one to run for X milliseconds and then switch to another for X milliseconds and so on. And then you determine that time slice that each task gets in FreeRTOS config, and that's decided like ahead of time before when you like compile your code. Yeah. Any questions on that? Sounds good. All right. I have an example now for scheduling. So if you guys want to um, open up that Git, GitHub repository that you cloned and go to the scheduling.c file. Yeah. Okay. So just let me know once you guys are all here. I'll just explain a little bit of what's going on in this file right now. So these are just some macros that we have to find. So task a name. We have, first of all, there's 2 tasks that are going to be created. And so we have a macro for the name, the stack size, and the priority. One important thing is that this stack size is actually not bytes, it's words. So we have a 4, like on our ARM46, the word size is 4 bytes. So this would be, like the number of bytes this would be would actually be 512 times 4 bytes for the stack. And since we're using like no heap memory, we statically define buffers for the task and the stack, since the FreeRTOS is gonna need like some memory to store like information about the task, and also to, like we mentioned, each task has their own stack. So this is where you define it, just like as an array. And you define that for both. And then here is a declaration of each task's function, callback function that's gonna run when we start running the task. So each task in this example, it just prints like hello from task A or task B, and then goes into a while one loop. So it doesn't block. It just starts like polling while one. And when we're creating a task, you use X create task static or X task create static, and it just takes in the function, and you pass in the name and the stack size. And this is an optional if you want to pass in any parameters into the callback function. You can do that here as well. You need to do that though. But like, let's say if you had like a mutex you want to be shared across different tasks, you can pass that in here. And then also define the priority, and you pass in a pointer to the stack as well as a pointer to the task buffer. Okay, so to run this, you can just do make directory build, and then cd into that build directory, and then you can run cmake base dot dot dash dc make build type equals scheduling. And once that sets up the config, once that sets it up, you can just do make dash j16. So, okay. Okay, I'll just delete the build directory. Okay, so make the build directory, switch into cd into the build directory, and cmake dot dot dash dc make. Okay, and then just do make dash j16 to build it. Okay, so if I run it, you're gonna notice an issue. Wait, so only hello from task A ran. Um, we never got any hello from task B. So so that's the first line in task B. That means that task B never actually ran. We're still running task A. Anybody have any guesses why this is happening? Either way, the same priority. Yeah. Yeah. Uh, that's part of the reason. So for Rtos, like the scheduler I mentioned is like that by default, but I've changed some stuff. So what part of the scheduler would we need to turn on?
Oh, so you need to like turn on the round robin.
Yeah, we would need to enable preemption because right now I have preemption disabled, so task A is still running. Because with if you have preemption disabled, that means that the task can't ever like lose processor time from outside of its control. It has to give it up voluntarily, either by like yielding or like trying to do something that's gonna cause it to block. But since we just go into a while one loop, it never explicitly gives up the CPU time. It never gets preempted. So if you go to the Rtos config file, there's a little macro called config use preemption. So if you make that 1, then it'll tell for your RTOS to use preemption. So if we do make it again with preemption enabled, and now I run that. So now both tasks ended up printing. So that kind of just shows you the importance of using preemption to make sure that all of your tasks run and you don't have tasks be just starving and never running. Yeah. Okay.
So what's the difference between the scenic build and the make?
CMake, when you do like CMake dot dot dash CMake build type whatever, that generates your make file to actually build it. That does like all the config and linking all the libraries and like resolving any like includes that you made that weren't relative to make the make file. And then to actually build it, you use the make file.
Why do you put dash J on the make file?
The dash J is dash J tells it when I do dash J16, that tells it to use 16 cores because it's just if you do it with make, it uses 1 core, it's just slow. So I just use dash J16, but you don't need to do that.
The actual CubeSat, like, do you have a single core?
Yeah, single core. But that's like when you're building it. So like that's when you're compiling it.
I see.
So if your laptop has 8 cores, you can compile it with all 8 cores and then flash it onto the ARM46.
So that's just for the compilation.
Yeah, that's for compilation. Yeah, because sometimes compilations takes a while if you have a big repo. Yeah. So, all right. Wait, did anybody have any other questions about that? Yeah. I'm gonna continue just to make sure we finish on time. Okay. So before we go on to mutexes, I just want to explain why they're even needed. So there's something called a race condition that happens whenever you have like a environment where you have multiple tasks running concurrently and they're trying to compete for the same shared resources. So this could be like a shared variable that both of them have access to, or it could be um, like a spy bus that both of them are trying to use. So for example, if we have 2 tasks, task A and task B, or 1 and 2, and they're both trying to increment a variable x. So if we're trying to do an increment, it happens in 3 steps. So let's say we have a variable x that's initially at a value of 1. If we want to increment it on our CPU, first we need to read the value that it has right now out of memory, and then we can increment it, and then we need to write it back to the variable to actually update the variable. So it's not performed in 1 step. So it takes 3 steps. So let's say we have task 1 and try to increment it. So it reads the value, and we said initially the value was 1. But now task 1 gets preempted, and task 2 starts running, and it's also trying to increment it. Oh wait, sorry. So task 1 reads the value of the variable and increments it, but it doesn't write it yet. Now task 2 starts running. Task 1 gets preempted, and task 2 reads the current value of the variable and it sees that the value is 1. And now we switch back to task 1 and writes the value. So now x is 2. And now we context switch back to task 2 and it increments it to become 2 because remember it stored a value of 1 from when it read it. So now it increments it to 2 and writes that back to the variable, and now the variable value is 2. But both of these tasks were incrementing it, and the original value was 1. So if it worked properly, in the end it should have been 3. but they both just ended up writing a two just because they were kind of like racing to see who can actually increment it first before the other one preempts them. So that's where race condition is. So yeah, since incrementing takes 3 cycles, if task A was preempted after reading X and task B uh, runs, the value that task A had read is not valid anymore because it's been incremented. But task A has no way of knowing this, so it just continues incrementing and writing that back anyways. So you have the issue of task racing to perform operations on the same variable. And so this can lead to like unpredictable outcomes that since you can't predict preemption, like you don't know when task one is gonna get preempted and task two is gonna start. Um, so you could like if you're trying to do this, you could get random things where you're like counting it's like 1, 2, 3, 4, and you just get like 4, 4, and then it's like normal again, and you get more like repeated and like other weird stuff. Um, One way to fix this is if you have like atomic variables that have atomic operations on it. So an atomic operation is just any operation that can be performed in one step without being stopped in the middle. So like if instead of having to read and then increment and then write it, if we could do all of this in one step and it couldn't be preempted in between, then we would be fine. So that's what atomic operation is. Like think of like like an atom. That just means that it's like indivisible. So an atomic operation is just an operation that can't be split. Okay. But since we can't always have all operations being atomic, we need another solution for this. And that's where mutexes or locks come in. So if we have a shared resource that's not atomic for all operations performed on it, we need to make sure that threads that are accessing it are like the access to it is mutually exclusive. And so that's where the name mutex comes from, just mutual exclusion. So mutexes are locks that you can lock and unlock atomically to make sure that only one thread accesses the shared resource at a time, even if it's preempted. So like task one would lock this variable, and so when it gets preempted and task two starts, it sees that the variable is already locked, so it can't do anything to it until task one finishes doing whatever it wants to do. It unlocks the variable again. So, quick analogy: like imagine if you had a washroom that you had to access with a key. So before going in, you try to take the key, which is the mutex in this case. And if it's not available, that means somebody else already has the key or mutex. So you wait for it to become available, which is just the same as entering a blocked state for your task. And then once the person in the washroom gives the key back, you can enter the ready state again and enter the washroom and do whatever you need to do. And then you might also want to like just give up if you have some other stuff to do. You can't wait all day to go to the washroom. You can just like give up and leave if it's been a while and you're still waiting. So that's equivalent to like setting a timeout, which you can do in Rtos when you're trying to take a mutex. You can say like if it doesn't become available in the next 5 minutes, then just give up and try something else. And so one important thing, this is kind of obvious, but like it'll become apparent why I'm mentioning it when we talk about semaphores. Only the person who has the key can give the key back. So you can't unlock the mutex if you weren't the one that locked it in the first place. Right. Any questions?
Since it isn't like anything, like with a sometimes the
If it's atomic, by
yeah,
definition, it can't be.
so it'll just take like it would lock it.
do you mean reordered?
I guess like I might cover it after this.
Okay. All right. So let's see a quick example. So if you go back to that same repo and go to mutex.c, this time to build this one instead of doing cmake, when you do cmake dot dot dash d cmake build type, um, after that equals the start point scheduling, this time put in mutex. Let's leave this up for a second so you guys can see. Okay, so you can run that command, and it'll set the new main to be this one. So run this mutex program instead, and then you can try running it by doing /workshop. Okay, that's good. Oh, true. Thank you. Yeah. Okay, so make dash j16. And you can do /workshop and run it. So this is like that example I showed you guys where we have two tasks and we have a shared variable x, and both of them are trying to increment it, and then they just print the value, and then once x reaches 2000, the task just suspends itself. Null is because with vtask suspend, it takes an argument of which task you want to suspend, in case you want to like suspend a different task. But if you pass in null, that just means like the task wants to suspend itself. So after the x reaches 2000, the task just stopped. So like, if we look at this, like obviously this isn't right. First of all, after 2000, we print out 3 for some reason. If I do this again, it'll probably be a different value. Yeah, so this time it's 80. So this is what I meant when I say you can get like weird, unpredictable behavior when you're using, or when you have a race condition. So I'll give you guys like 3 minutes. 9:47. I'll give you guys till 9:51. You guys can try to see how this can be fixed with mutexes. Um, so I'll just show you guys quickly how to create a mutex. Actually, so if you add in to the top static semaphore underscore t, let's call it x mutex, and then you can create another static variable called semaphore. That's a semaphore handle type called x mutex handle. And handle is just means it's like a reference that you have to the mutex. So you use a handle to access the mutex and do anything you want to do with the mutex. And then if you go to main, you can use x semaphore create mutex static, and then just pass in a pointer to the buffer that you declared, which is x mutex. It should have been buffer. X mutex buffer. And then assign the return value of this to the x mutex handle. So that now x mutex handle has a reference to the mutex that you created. So see how you can use this mutex now to make sure that this race condition doesn't happen. By the way, if you want to lock a mutex, x semaphore take mutex buffer, no mutex buffer, mutex handle, and to give it, this is x semaphore give take also has take also has like a block time argument, so you can just make that before max delay to say you'll block forever until you get the mutex. That's what I was saying before about the timeout. Like if the key isn't available for like 5 minutes, they might just give up wanting to go to the washroom and do some other stuff. Okay, so I'll give you guys to like 9:53 to try this. I'll give a solution after that.
Sorry, could you show again what commands need to run in the terminal? Please?
Sorry, could you repeat that?
Could you just show again what commands need to run in the terminal for the CMake commands?
Yeah, sure. So first, if you're at the root directory, you can do make dir node, and then cd. It's not working for me because I haven't made, but then cd into the build directory, and then you can run this command right here, cmake dot dot dash d cmake build type equals mutex. And then once you run that, you can do make dash j16 to build it. And then you just do dot slash workshop to actually run it. I got some here, mess something up. What did I do? Oh, it's because I called this out here. That's why. But yeah. Were you able to do it, or do you want me to show you?
Yeah, that's good. Thank you.
Sorry.
Oh no.
The handle type is semaphore handle underscore t, and then buffer is static semaphore underscore t. I'll give you another minute for the solution. Actually, we're kind of running low on time. Sorry?
So is the intended solution for it to just go up to 2000?
Yeah.
Okay.
If it's working, like incrementing normally up to 2000.
It's incrementing up to.
You could also just change the if statement to like here, equal
Yeah,
just to be
that's
safe.
what I did.
Okay, so the way to protect this, you want to make sure that all of your accesses to X are covered within the critical section. So critical section is just that like section that of code that you have where you took the lock already before you give it. So if I do if X semaphore get on X handle and delay PD. You don't need to do if PD pass using for max delay, but if you're not, then it's good to use it. Or you should use it if you're not like waiting indefinitely, because then it could fail if you have a timeout. PD pass means that you took the mutex and you didn't timeout. Otherwise, if you weren't able to get the mutex and just timed out, it returns PD fail. But that doesn't make a difference here because we're doing core max delay, which means we're gonna wait forever until the mutex is available. And then so here we take the lock if it's available, and then we do whatever we want to do with X. And then afterwards, once we're done all of the stuff we wanted to do with X, we give the mutex back and unlock the lock. And do the same thing with the other one. So now, if I run this code, hopefully it builds. Okay. And now if I run this code, you'll see it's incrementing normally, as it should be up to 2000. And we're not getting that weird thing anymore where we have random numbers in here popping up. Okay. Yeah, so back to the slideshow. Almost done. Slideshow. Yeah, not many. Just a couple more. Alright, so similar to mutexes, we also have semaphores, but these are usually used to like signal and communicate between tasks instead of just like trying to prevent race conditions. They have more use cases. They're usually used to synchronize tasks. So we'll talk more about that in a bit. So it's kind of like an atomic integer that you increment when you give it, and you decrement when you take it. So if you try to take the semaphore but it's already 0, then you get blocked. Otherwise, you just decrement the value and you get the semaphore. So there's two kinds of semaphores. You can either have binary, which can only ever be 0 or 1, which is kind of similar to a semaphore, but not exactly. I'll mention in a second why it's different. And then you can also have what? Binary semaphore is different from a mutex, but yeah, it can only be 0 or 1 like a mutex. And you can also have counting semaphores, which the value can be anything. So I can just do like X semaphore give like 100 times, and the value will be 100. And then you can just take it 100 more times before you ever get blocked. And it does, yeah, so it doesn't need to be taken before, like you can give it multiple times before it's ever taken. So imagine like another analogy, imagine you're trying to go down a slide at a water park. So the lifeguard or like the task will give a thumbs up, which is like a semaphore, whenever the slide is free. So the first person to try to go down the slide will like kind of take control of the slide or take the semaphore. So now if somebody comes, they need to wait or block until they get a thumbs up. And then the lifeguard, which is another task, once they see that the person finishes, they'll give the thumbs up again or give the semaphore, and then you can go down the slide. And one thing to note is that the lifeguard never took the semaphore, but I was able to give it. So that's the main difference between a semaphore and a mutex. Even if you're using a binary semaphore, mutexes have ownership. So I mentioned before how you have to be the one that locked the mutex to be able to give it. But with semaphore, you don't have to take it. You can just be giving the semaphores, and another task can just always be taking the semaphores. You don't have to be the one that took it to be the one to give it. So, for example. Okay. Wait, any questions about mutexes and semaphores? Sounds good. We'll do it in QA, I guess. So another way that you can communicate between tasks is using queues. So they're different from semaphores because you're able to pass more information into a queue. So you can add items to a queue that will be received by any other task. And whatever items are added first, you get to leave first, just like a regular line. So like imagine like we have Laziz and there's people trying to get Laziz. If George comes in here first, he goes at the front of the queue, and then next person goes behind George, next person goes behind them, and Laziz will just take the person from the front, take the order, and then take the next person, and so on. So it's called like a first in, first out data structure because the first one to come in is the first one to leave the queue. sending to and receiving from the queue is always atomic because you want to have a race condition happen. And receiving from or sending to a queue that's like empty or full respectively. So like receiving from a queue that's empty or trying to send to a queue that's full will cause the task to block. And like mutex is semaphores, you can set like a timeout time in Rtos for how long you want to block for before you give up. And they allow you to give more info than a semaphore because now you're actually passing some piece of data into the queue that's going to be received by the task instead of it just taking a semaphore. All that it knows is is that it was given, not that like anything else. Okay, so going back to the repo, we have another queue example. So same thing, same build steps as last time, except this time you're going to use cmake dot dot dash cmake build type equals q. So instead of mutex, just use q. And so I added some user code start and end. So there's three places where you need to add some code to this. And you guys can try that. Sure. Okay, so we have an enum here, and it just has null event, increment, print, and hello. And this is where we'll be sending into the queue. So whenever we're sending something into the queue, it will be this enum. Um, so in our main, now we create two tasks, and then we also you need to add the code to create the queue. Actually, I'll just do that first. If we have time. So you can use xq create static, and then yeah. So task B queue length, and then task B queue item size, queue storage would be the queue stack, and then we pass in the buffer for the queue. So you might be wondering like what's the difference between the buffer and the stack? Because like Rtos needs to manage these queues, the stack is where all the messages that you pass into the queue will actually go. But Rtos needs to store some data, like metadata for managing the queue, and so it puts that like the handle and stuff. So it puts that to this variable here. So task gauges receives from the command line some strings, and then based off the string, it sets a enum, and then it sends that event to task B to handle it, like I mentioned in these comments. So I'll give you guys to like, let's say 10:08 to do that, and then I'll give the example, and then we'll finish off. I don't know if there's any like Rtos functions you need to use, and you don't know like how they work. Rtos has a lot of good documentation, so you can just search up like Rtos Q, VR or like Rtos Q send, and it will have like a page explaining it and all the parameters and everything. So just again, like there's three sections of that, and there's a comment explaining what you need to add. Okay, I'll give you guys another minute. If it's working properly, you should be able to like run it in command line and like print increment and hello.
how do you input each of them?
Type it into the command line, like increment printer hello.
Yeah, I'm trying to like print that thing out, but it's not.
Yeah, sure.
I had a quick question, Navtaj.
Yeah. Hear me?
Uh, can you hear me?
Yeah.
Yeah. Actually, I basically it's not much to do with this current workshop, but I kind of skipped over to the actual challenge of the onboarding instead of setting up Windows subsystem for Linux. And I was wondering, like, which distribution do you guys use for WSL?
We don't like for actual repo. It's Dockerized now, so we don't use WSL.
So you can run Docker in Visual Studio.
Yeah, for actual repo, but for
Okay.
this, just use wherever you have CMake set up, and download it.
Okay.
See somewhere.
And so can the onboarding challenge be also built inside the Docker container, or
The onboarding challenge you can just do on your whatever OS you're using, I think, or wherever you have CMake. We don't have the onboarding isn't Dockerized.
okay? Got it. Thanks.
Okay, so hopefully you guys have time to try it. I'll just go over how to do it real quick. So first we want to send the queue to task B. So you can use um, xq send task B queue. Is it still frozen? Oh. Okay, can you guys see this now? So xq7 and then pass in a reference to event send and just wait indefinitely with permission wait. So now we'll receive some kind of command from command line, um, and then set event to send according to that, and then send that to task B to handle. And know how we in the priority I set task B to be priority 2. So since we're sending the queue here, this way as soon as we send with the queue, it'll unblock task B since it's higher priority, and task B can handle whatever we send. So now in task B, um, we can define command line event, this is the event, and then receive from the queue. That slow. Receive from task B queue. Put that whatever we receive into that event variable, and just wait forever. I'll just say if that didn't work, that failed for some reason. increment, then just plus plus, and make sure to break at the end of your case statements, just so it doesn't continue on running the next ones. And then print, we just want to print print and so what is your gotcha. Otherwise, we'll just print here about. So now, if I run this, hopefully it should work. Oh, yeah. I forgot that was called a handle, not Q. Okay. If I run this, say hello.
Like,
This was working. I ran it before the workshop.
like it doesn't even like I put a print statement in the very beginning of main and it doesn't print that.
I think this should be it. This should make me. Yeah, it's pretty low. Um, I think all could be going on. Okay, we're already over time. I'll I'll send the working example later. I don't know why it's not working. I tested it before and it was working. But yeah, the general idea is it was about the queues. So once we receive hello, it'll send it in this queue and it'll unblock task B, and then task B can deal with it then. So I'll figure out what's going wrong and then I'll send that in firmware general. Okay. Alright, that was the end. Now Q&A. If anybody has any questions, feel free to unmute. Semaphore. So semaphore you use to synchronize tasks. So it's like with a queue, you know how you do like execute send, execute receive. With semaphore is like it's a kind of like similar to a mutex in terms of syntax. Like you can give and take a semaphore, except any task can give it, and any task can take it. And you can have counting or binary. So instead of mutex is either locked or unlocked, semaphore is like a counting variable. So like if I wanted to to like the side example, like if you're waiting to go down the side, it's like you're waiting to take a semaphore, but right now it's at 0. So another task like me could give you the thumbs up and give the semaphore, and then you can take it and go down. So that's like the semaphore is a way for me to communicate with you with another task. That's some like event happened. And so if we don't need to pass any like data like an enum like we did with the queue, like if we just need to say something happened, you can continue now. We can use the semaphore. I don't think so. I know.
Like you could make it queue at the same time.
Yeah, semaphore. I think in FreeRTOS uses something similar to a queue, but queue. Yeah.
Yeah, but I think like the main idea of the semaphore is that like you initialize it with like a certain number.
Yeah.
And then like every time you
Yeah.
I don't remember the Rtos.
Yeah.
And then every time you post it increments that number, and if it's at 0, you semaphore. So it's like if there are 10 items in the quiz example, you can't get the 11th item. You need to wait on that. Not like it needs 10. Size it to 0, but you put like one item inside, then it's gonna. Other thing comes and waits on it, they get blocked because. So it's like you need to like what's the Rtos thing for posting?
Semaphore give, semaphore take.
Yeah,
It's the same ones we use for mutex.
Yeah, so I think like you need to give more times than you take.
Yeah. So give will increment the counter and take will decrement it. But if the value is 0 already, you'll get blocked.
Like setting initial size for the.
FreeRTOS doesn't let you set an initial count, but you can just like give it as many times as you want to set it. I think FreeRTOS initializes it to 0 by default. Yeah. Any other questions? All right. Thank you guys for coming. Hopefully, you guys learned something. I'll see you guys later.